All right, everybody, welcome to the last session of the pre-course on the mathematical foundations for the PhD school next week. And so Pieralberto, please take it away.
So, this last lecture concerns bundles. So let me first start by giving some intuition why you need bundles. Let's consider, for example, the Newtonian space-time. With Galilean relativity, which means that we consider the fact that we have independent inertial observer, they have the same physics. And now let's draw this space-time, of course, because I don't have 3 + 1 dimension with 2 spatial dimension. Well, then let's imagine that t is the time axis, and yes, and imagine that you have a fixed t, you have your space. And now you ask when I can identify the point in space at different times. That will depend on the observer. So for one observer, the point in space can be identified that way because he moves in this way. But for another observer, this point can be identified later on with this point because he moves in that way. So there is no absolute identification of a point in space. But instead, the projection at what is the time, everybody agrees at point in space at different times. Whereas there is a well-defined projection of points in space-time to time. A similar situation, it's less physical, but it's also very convenient to discuss, is a case in which you consider a strip, let's say of length 2, and let's say 0 is the mean value, and you join the 2 extremes of the strips with opposite orientation. So you have some circle, because when you identify this point with this point, you get a circle, but the other point will be twisted. So join the extreme with opposite orientation, as is written here. So what you would get is something like, because now it's a question of how to draw it, but anyway, something like this. In which you have your original circle, which goes like this. And this is called a Möbius strip. And now also you find something interesting. You have a point in this strip over here. And the projection on the circle, which is the point in the circle which corresponds by projection to this point, is absolute. Let's call S1 this. S1 is absolute. However, the sign of the vertical coordinate is not absolute, because what is over or below depend. You see, there is no absolute meaning, because when you attach, this could be interpreted both ways. So this mixture of absolute data a projection of, let's say, relative data give rise to the idea of a bundle. So what is more mathematically a bundle? Then you can recognize the above as a bundle. A bundle is a triple where there is a space E, a projection pi M, where projection is from E to M, and E and M, this is this is called total space, this is called base space. In general, it could be E and M could be topological spaces or manifolds. And this is the idea of the bundle. And if you consider the inverse image of a point in the base space, it's called a fiber. So it's a fiber at P. If you consider the previous two examples, the pi minus 1 of T in the first example is a space time T. Whereas pi minus 1 of a point X, let's say a point X in S1, is the interval minus 1, 1.
Yeah, but you're outside of the camera range.
Okay, I should be. This is fine?
Yes, thank you.
So now it should be fine. Okay, so you see, I mean, you have given two examples. One is from physics, the other is from mathematics. Of the relevance of this idea, you have a bundle. And this is a general concept, but most of the time you will discuss not generically bundle, but what they are called fiber bundles. So it's a bundle in the sense that I discussed above.
Professor, you have to lower the page now. Yes, thank you.
Okay. Why I don't am able to get the full space? Unfortunately, I have very few time today before the lecture, because I have some examination, so let's hope that's fine. Okay, so anyway, you just tell me if there is problem in. So a fiber bundle is a bundle where each point of the base space has a neighbor let's call, for example, as we said, usually UP, such that pi minus 1, so the inverse image of this neighbor is, let's say, diffeomorphic for manifold, which most we discuss manifolds. If you discuss generically topological space, it will be homeomorphic. so topological space, to the neighbor itself times F, which is the fiber. So what's the idea in the Möbius strip? So we have the Möbius strip interpreted as a strip with two orientation opposites at the boundary. You cover them with, let's say, two open sets. One open set will be the red one. The blue will be the other one. Remember that these 2 points are joined.
I have a question about this.
Yes.
Are the fibers generically all the same or all homeomorphic to each other for every point?
They are in the fiber bundle, they are homeomorphic to each other or diffeomorphic to each other, yes.
Okay, thanks.
In the bundle, it is not necessary. And now the idea is that, okay, here, one of the two intersections, you attach with opposite vertical orientation. So if you have the strip in one of the two superposition, you just touch with opposite vertical orientation. Then it's clear that each of these open sets of the circle, so you have your circle here, you have the pi minus 1 of the open set here on the pi minus 1 of the open set here of this and you see clearly that you can be written as the open set times the interval minus 1 1. So here one you attach with opposite and the other one you need to attach with the same orientation. Vertical orientation. Okay, so since locally a fiber bundle, so now from now on we'll discuss only fiber bundle, and as I said, a fiber bundle. As I said, we mainly concentrate on the case in which the space are manifolds. So is diffeomorphic locally to some U cross F. The idea is the same as for the manifold. That are locally like some Rm. And so the idea is attach different patches and use what they call local trivialization, which in this case is the analog to the chart that we use in the manifold. So what are these local trivialization? You can imagine the inverse image of, let's say, an open set UI. You map it to UI times the fiber F. The inverse image of uj, you map into uj times F. And of course, you have to give a rule for a point P, which is in the intersection of ui and uj. You give a rule, let's call Fij, which sends the fiber, let's say Fi, above pi minus 1 of ui to a fiber Fj, which is above pi minus, is in pi minus 1 of uj. In the following way, you define your Fj as Fij of the point P, so times acting on Fi. So you should give me a rule, a map from the fiber to the fiber, one thought above in the open set UI, the other above the open set uj for a same point P, that give me a rule to attach the two fibers, which are the properties of these maps. Fij is equal to the inverse map minus 1 ji, so this Fij, of course, they are invertible. And Fij times Fjk times F are equal to F Ik, which for a point P, which belongs to UI intersection uj intersection uk, which is the same using this property, say the Fij, Fj k, Fki equal to the identity. So let me think, you have your point P, you have a fiber over P, let's call F this fiber. You can think we have one point which is considering the above the open set UI, then you get some Fij which maps in the same fiber in a point which is thought to be in the inverse image of uj. Then you map again in the same point which is thought now to be in the inverse image by pi of uk, and the idea is, of course, that if you go from here to here and from here to here, it's the same as to go from here to here. So very simple idea of how you join the. Okay, there is one special
Can you
case.
leave the page for one more second,
Sorry,
please?
sorry, it was too fast. Sorry. So please tell me when I should move it.
Fine, no, thanks.
Okay. Now, there is a special case, of course, if the total space is just given by the Cartesian product of M times F, the fiber bundle is called trivial. It can be checked that this happens if you can write your Fij as Hj to the minus 1 Hi, where Hj and Hi are, this is defined in Uj, this is defined in Ui. If this is possible, why? This is give you a trivial bundle, because originally you have Fij of P times acting on Fk give me Fj, but now using this I can rewrite that Fi times Fi is equal to Hj times Fj, which means that in the overlap, and so it means that there is no twist in some sense. Everything is extended smoothly along M. But this is not always the case. Let me think an example. Suppose you take as a fiber the complex numbers, and Fij will be some multiplication by some phase e to the I phi ij. Then, according to our rule, e to the I phi ij plus phi jk plus phi ki must be equal to 1. But as you know, this does not imply that f by j plus fjk plus fki is equal to 0, because it could be any actually 2 pi times z. And so this is 0. In fact, if phi ij is equal to some phi I minus phi j, then it is automatically 0. But in general, it's not 2. So it's clear that hidden in this triple intersection, there is some information of non-triviality of the bundle. Let me give you another example of non-trivial bundle. By drawing, okay, this is the tangent space. We'll come back again on this. It is tangent space of the two spheres. The total space is, which is written as T times S2, is just the union for all points P in the sphere of what we already defined, the tangent space at point P of the sphere S2. The base manifold is just S2, and the projection is made like this. So you take a point V, which belongs to the tangent space of the two spheres at point P, and just project into P. So you see from here that the fiber, as somebody of you mentions, is the tangent space of S2, which always are diffeomorphic to R2. But the tangent space, the tangent bundle to tangent bundle, this is a tangent space and this is a tangent bundle, sorry, I just mix up. The tangent bundle of S2, but the tangent bundle of S2 is not just S2 times R2. How you can intuitively get this idea? Suppose you have the two spheres and you pick a point in the sphere and you have your tangent space here. Of course, you have many tangent space. You pick another point, you have another tangent space here. Of course, they are entirely R2, but it is clear that. But now suppose you want to construct a vector corresponding, let's say, to this tangent space, and you choose this vector here. Then you want this should move smoothly because everything is smooth here. So if you choose another point here and a tangent space here, maybe you want to that this vector is this one. You take this point, you take this vector is this one. You arrive at this point and the vector is this one. If you want to be smooth, but still keeping this vector here, you could choose another idea. Well, you move that way your vector, also smooth. But when you arrive here, you see these two vectors, they have opposite orientation. And this suggests that, in fact, you cannot do it globally. So S2, the tangent bundle of S2 is non-trivial bundle. Can I move?
Yep.
One question.
Yes.
So maybe this is already going where you're going. Does every bundle which is non-trivial necessitates the notion of a parallel transport?
No, this is not, it is an additional notion
Okay.
that you can put on the bundle.
But if I were to compare these two vectors as you draw them now, I would need some notion of a connection or...
Yes, right. In
Okay.
order to get the point of this drawing is that there will be no any way you can do it.
Okay.
You can try to, because if you smoothly decide to move, depending on the way you move, you arrive here and not find always the same result.
Yes.
So let me now introduce a new notion, which is a section of a bundle. So given a bundle, let's call E by M a smooth map S from M to the total space, from the base space to the total space, such that if you first apply this section and then you apply the projection, give rise to the identity. It's called a section. And a section, it generalizes a smooth function. So let me see why. So usually you draw it like this. E projected down into M by projection pi. And now you find some map S which goes from M to S and satisfying this property. Let's suppose that E is trivial, so it's just M times F. Then, of course, this map S can be seen as a smooth function from M to F, because remember, in this case, you have E is isomorphic to M times F. M goes into up to section S, but according to this rule, you do not change the point above which you move on the fiber, because you have this condition. And so there is one point which is mapped into itself here, so you get no information, so it's just basically a map from M to F. But suppose you consider the Möbius strip. So you have the Möbius strip. So you have join again with opposite orientation. You have your circle here, you can think as a base space. And now a section, necessarily if it is smooth, this point here, because of smoothness, must go here by smoothness. When you join, they should go. So the section is something like this. But then it clearly is not this section is not a smooth function on S1, as you would expect. So if E would be S1 times minus 1, 1. Because, of course, it's obvious that from the point of view of a function, you cannot, remember that these are identified. You cannot think a function in which in the same point give rise to two values. So it means that this is not a function. So let me discuss, mention some special cases of fiber bundles. Suppose you consider a total space E of the bundle with your fiber, which is a vector space. Well, this is what we call a vector bundle. In the special case, if V is one-dimensional, so for example, R or C, like isomorphic to R or C, then we speak about a line bundle. Let me give an example of suppose the tangent bundle that you already mentioned. Tangent bundle. So you have your manifold M, and you consider the tangent bundle of M, which is given by the union for P in M of the tangent space at P in M, the projection and M, like as we have done in on the two-dimensional sphere. Then you can, of course, now you understand the trick, you can construct a cotangent bundle. Which will be noted by T star of M, which is the union of P belonging to M of TP star of M by M. And now, of course, more general, you can construct tensor bundle. Suppose you have considered a tensor bundle with R covariant, contravariant indices and S covariant indices. Of course, this is the union of P in M of what we discussed in the first part of the note, the tensor space at the point P are contravariant S covariant. Can I
Can you
move?
move the page a bit outwards? I can't read
Sorry?
everything. Thanks. In your last expression, don't you also need the tensor space to depend on the cotangent space?
Yeah. Of course, this it depends both on the tangent and the cotangent the bundle. Yes, but
Okay.
you see that the reason why you when you have identified your vector space, everything is fixed. The cotangent bundle of so automatically you have the dual space, so that is fixed.
But you need some notion of connecting these two, the dual space and the via some
No.
scalar product.
No, not necessary. No.
But don't you need
you can define independently on the concept of scalar product.
Okay.
We have seen, because the dual space is just defined as to be the functional which are linear on the vector space you start from, right?
Yes.
So this doesn't need a scalar product. If you have a scalar product, okay. Well, now you have a natural identification of the vector in the tangent and cotangent space.
Yeah, this is what I meant.
But this is not needed a priori.
Okay. Yes, okay.
Okay. So still other okay, tangent. Let's consider in particular, if we consider for antisymmetric R covariant tensors, you can consider the okay, I forgot to say one thing, and that's okay. If I have a bundle, sorry, so I should start again. I missed one notion. If you have a bundle E, you denote by, so E pi M, you denote by gamma of E is the space of sections of the bundle. So this is a very reasonably universal symbol for the space of section of the bundle. So in particular, now I should write, in particular, for antisymmetric arcovariant tensors. So we know that locally, if we have a function, I mean, the antisymmetric arcovariant tensor which depend on points on antisymmetric arcovariant fields, these are nothing but forms, are forms. So the sections gamma of what we denote by lambda p, lambda r in this case. Okay, let's call p because we usually letter p of t star of m. Well, so which is the antisymmetric tensor product of t star of m. Well, usually in many cases called omega p of m, and which are, I mean, this section is just the space. So the sections in, okay, are the p forms on M, generalizing their definition, which were given, remember before, either in Rm or in the domain of a chart. And now you remember that one of the important property of the there are basically two reasons to introduce this. There are very natural transformation properties, and the other is that you can integrate them. Okay, so let's discuss the. Imagine that you can generalize the integration that we have discussed in Rm into or a surface in Rm as an integration of p forms, which are now defined on a general manifold M. So what is the trick? We already know how to integrate p forms on a p-dimensional surface in Rm, to integrate on a p-dimensional manifold now. So you don't want to go out of this manifold. We use the usual trick. What are the tricks? Of course, charts. And as we have done already in the case of the surface, the pullback. So now we need to generalize the pullback that we have defined originally for forms in Rm to the situation in which you have a bundle. And so you introduce the notion of the pullback bundle. So given the bundle E pi m and the map phi from two manifold n to m, we can construct the pullback bundle which is denoted by frequently like phi star, which phi, remember the map. Then you have some projection, which probably write enough phi n in the following way: the total space phi star of E is equal to the set of pairs n and u, which belongs to small n and small u, which belongs to n times c, such that the image of an element of n, your manifold from which you start, is equal to the projection of a point P in the total space of the bundle E down. So now it's again an element of M. So let me maybe make a picture. So you have N, you have a map phi. You have a map N, you have a map phi to M. Then you have a projection from E to M. That's called pi. You can have also sections that we discussed later from M to E. And then you have your bundle phi star of E above N, which is constructed in this way. It's a very constructive way. And of course, this has its own projection, phi of phi. Why is this pullback bundle is important? Because if S is a section of the original bundle E, you construct a section which is phi star of S, which sends a point N which belongs to N to N, and the second should be an element of U, so it is just obtained by taking your point N, you map to M. S was a section in E, so from M to E. And this gives me, according to this, section is of phi star E, the pullback by phi of the bundle E. So if I have a section here from M to E, you use this construction and you get a section phi star of S from N to phi star of E, which satisfy precisely because of this definition of the property of pi composed S must be the identity in M. Automatically phi satisfy on phi star of S the identity that this was in M and this is in N. So now we have constructed, given a map from two manifolds, you construct a pullback, and you have a bundle on a manifold, you construct a pullback bundle on the first manifold. Can I move?
Yes, from my side.
Okay. So now how I integrate? We start supposing the simplest case. Let's first suppose that your P form, let's call alpha P on M, which is P-dimensional, has a support on an open set UI of a covering of M. With chart phi I. Okay, then we can construct a P form on phi I of UI. Remember that phi I was a chart, so it maps an open set in the manifold in some open set in RP. using the pullback bundle. How? Well, so we have a map phi I of ui. Remember that phi I was invertible. So definitely we have the inverse map, phi I inverse, from phi I of ui, which remember was a subset of Rp, to ui, which was a subset of M. And now you can construct the bundle lambda p of t star of ui, which is whose sections are precisely these p forms on ui. And now we apply the previous construction. This was a map from a manifold to another manifold. You have a bundle on it, so you can construct the pullback bundle. And the pullback bundle will be phi I to the -1 star applied to the lambda p of t star of ui. And now the section, we already know that a section here, so p form here induces a form here. And now you have a form which is defined on phi I of ui, which is a subset of Rp. And now use the usual definition, define the integration over ui of your p form alpha p. By definition is the integration over the image phi I of ui of the pullback. So now we know what to do for a form which has a support on an open set of a covering. Now you remove the assumption of the support so that alpha is a p form in N. So how I can remove this? We introduce a new concept, a partition of unity. What is a partition of unity? It's a set of functions, let's say labeled by some index set, which are positive, so they are real functions, C infinity on the open set ui, such that the sum over I belongs into the index set big I of rho I of a point P are equal just to 1. Then you need that for each point P only a finite number of rho I contribute, okay? So let me explain what it is. For example, consider a piece of the real line which you have two open sets. One open set is, let's say, ui from here up to here. Another open set is uj from here and go here. And now you construct something like this must be 1 up to here, and then it goes down. It should be 0 here. Conversely, for the other one should be 0 here when there is no we are outside of uj, goes up and becomes 1 when you go in uj, in such a way that here the sum of the two is always 1. And now it is clear how you do. You define alpha I is equal to rho I times alpha. And then you set the integral over m of alpha just as the sum over index set I of the integration of phi I to the -1 star of alpha I, which each one is contained exactly in phi I of ui, and then you're done. This way you are able to define an integration of a P form on a P-dimensional manifold without using embedding in higher dimensional spaces. Can I go? Can I move?
Yes.
Okay, let's now suppose that you have a manifold with a boundary. Fm is a manifold. Remember, we defined what it was a manifold with boundary. Boundary of M. Since you can check easily that the pullback, maybe we already mentioned, commute with exterior derivative, and our alpha was just, if you look back to the sum of the individual alpha I, which have support only on UI, well, by definition, d alpha is equal to sum over I of d alpha I. And now it turned out that you can extend the Stokes theorem, extended to M. How? Suppose you integrate d alpha over M. By definition, this is the sum over I, integral over phi I of ui of phi I inverse pullback of d alpha I. But according to this rule here, you can also write this as sum over I phi I of ui d exterior derivative of phi I minus 1 inverse alpha I. But now this is contained in RP. So you can apply standard Stokes theorem. It's the usual that you already know. So this is also equal to the sum over I of the integral of the boundary of phi I of ui of phi I minus 1 star alpha I. But now you can, the boundary of phi I of ui is the image of phi I of the boundary of ui. So it's the sum over I of the integral of phi I of the boundary of ui of phi minus 1 I pullback of alpha I. But now you recognize that this is nothing but the integral of the boundary of M of alpha itself. And so you have extended Stokes theorem. Okay. So an important generalization, I don't know if I will arrive at it, but anyway, I try. An important generalization of P forms are what are called the Lie valued P forms. So let's start a general construction. So given E pi M a vector bundle, so the fiber is a vector space, we can construct the following E tensor product, the wedge product P times of the tensor of the cotangent bundle of M, and the sections of this object are called E-valued P forms. In particular, the one I will be interested, if E is equal to, E, as you see, can be generically a vector bundle. Well, certainly a vector bundle is M times the Lie of G. because remember this is a vector space. So this is definitely the trivial bundle on Lie of G from M. Then the sections, so we denote by gamma of M times Lie of G, tensor product with lambda P of P star M, which usually are denoted by omega P of M Lie G, are called Lie G values P forms. And a wedge product, of course, this is interesting only if the wedge product is defined on them. But the wedge product among them is defined by, suppose you have A and B, which are element of Lie G, AP and is a P form on M, and BQ is P for Q form on M. Then an element you can write like E times tensor product AP, wedge B tensor product BQ, by definition is the Lie bracket of A and B, tensor product, the wedge product of AP and BQ. You can check that this has all the nice property of the wedge product. Can I move?
When you last said that this has a nice property of the wedge product, you mean this entire structure, including
Yes.
the
So
Lie bracket, has now a wedge product structure?
Yeah.
Okay.
You have
Okay.
both. They are compatible in some sense. You can see also from here, you basically define the wedge product in such a way that separately you take the Lie bracket on the Lie element, the algebra, and the wedge product on the forms.
But like intuitively, maybe I'm mistaken. I have two antisymmetric things, and if I exchange the left-hand side,
You should consider both the change due to the fact that you have the character of the forms, and
yes.
also you need to make the commutator of the element of the Lie algebra. So when we write the wedge product, you include both operations, the wedge product of the P form part and the Lie bracket of the element of the Lie algebra.
So I still get this antisymmetry due to this -1 to the power of P times Q.
You keep, but you also
Okay.
should keep the information that you have the commutator.
Okay, then I have to
Which means
calculate.
that this you can write this in the basis. Okay, suppose you have a basis E alpha E beta. Let's say is a basis of this will be F alpha beta gamma E gamma, right? So you get some additional F
I see.
alpha beta
I see.
gamma.
I see. Okay.
So another important fiber bundle is what is called a principal G bundle. So let's denote by P, usually P, pi, and M. And if G is a Lie group, you require that there is a right action. Remember that last time we defined what is a right action is of G on P. So we have an element G which belongs to the Lie group G, and you construct this action, which is called RG, the action. And you want to this action, which is transitive. So you have only one orbit and free, which corresponds to a trivial isotropy group. So let me write in formula. RG is a map from P times G to P, which send your point U, which belongs to P, and G into act on U by G, and as we have done, usually you just write it simply as UG. And with an additional property, with RG respecting the fibers. So it means that you want that G acts only on the fiber. RG, you have a P, you have your fiber, pi minus 1 of P, and RG acts on the fiber. So in formula, pi of U of G, because this was a point U of your, which belongs to the big P, you send it here like is UG, but you want that the projection of UG is also equal to the projection of your starting point, U. It's almost clear that if you can generalize this construction, if D is a representation of G on a vector space V, we can construct what is called an associated bundle to P in the following way. The total space of the bundle E, which will be typically denoted by P times with sub-indexed representation of your group V, is the set of all pairs where U belongs to P, V belongs to the vector space V, which are in the equivalence class, which is determined by D. U, so U you can identify with U, the couple UV you can identify with the couple UG, and the representation of G inverse acting on V. Everything is well defined here because you see V is an element of the vector space V, which carry a representation. So this is a representation space. So D. So V is a representation space for D. So this is well defined. It's a still a vector of V. This now is a point in P, and so this is a well-defined bundle.
I have a brief question. When you mean representation space, what is the difference to vector space on which the representation acts on?
Yeah, it's the same.
Okay, it's just
By
the
definition,
same.
a representation space of a representation is the space, the vector space on which the representation of the groups act.
Okay, I'm confused.
Can I move?
I think
Yes.
so.
Mhm.
Fine? Okay, so now finally come to this idea of connection. Okay, now we consider the tangent space of the total space, which of a fiber bundle. So just usually say the tangent space of the fiber bundle. So the vectors along the fibers define uniquely vertical vector space, or define uniquely vertical vector spaces. Let's call du corresponding to the point u in the total space E of the bundle. And the other vectors? Yes, to get an intuition, why one is absolute and the other is not. Let's think to the Newtonian space-time. And different inertial observable. Okay, so I just now wrote to simplify, the drawing will be with one space dimension. This is already, you get all the information from here. So we have discussed already this. You have an axis T of time. Now you want to represent in the same diagram two different observers. So one has a space at constant time, this line. Another one must have the same space as constant time. The present is the same for all the observers. But suppose that you have one observer which moves with respect to this with some velocity v, then of course its world line in space-time would be a straight line which is inclined with respect to this by the velocity. But according to so you have two observers, okay, one is this, but of course you can consider an observer, an inertial observer, which consider himself as fixed in space, which is the one which follows this line. So it means that if this is the time axis for the red observer, this is the time axis for the blue observer. Now, we have already said that the time is the same for every observer. So we know that this is a fiber, so it is fiber is a space at fixed time. And for both observers, this here is a vertical. Remember that the base space now is this. It's a vertical vector both for the observer blue and for the observer red. But if I want to have a vector which is horizontal with respect to the base space, meaning that correspond to something which do not move in space, well, the observer blue will say that this is a horizontal vector. But the observer red would say that this is the horizontal vector. So you see that in a bundle, in general, you have a well-defined definition of what is a vertical space of vectors just along the fiber. But what is an horizontal vector? Well, this depends on. So we need to specify it, to specify the notion of horizontal. This is if you want with respect to the base. One needs an additional structure. And the structure is the connection. And to me, somewhat surprisingly, is related to the gauge field. You will not recognize immediately this relation with the gauge field, but it will come, I hope, to arrive to that point. So what is a connection in very general situation on a fiber bundle? So very general. E is a collection of subspaces. Let's call HU for every point U in E, which are subspaces HU, which are contained in the tangent space of E at U, with smooth dependence on U, such that your tangent space of E at U can be written as a direct sum of your horizontal space, and this is the absolute, vertical space at U. Remember that vector V, which belongs to the tangent space of E, is in the vertical space if, so you see, you don't need any construction, any additional information. It's just the pullback, the pull forward of this vector of the projection is 0. So you don't need to define a vector, what is horizontal, you don't need any additional information. I think that this example makes it very clear, the Newtonian space. Can I move?
Yes, on my end.
So now let's do a kind of a picture of what we discussed. So you have your base space, you have your fibers on the base space, and you have declared that, okay, we have the vertical space. This is easy, always like this, along the fiber. And now you have declared some space which are horizontal. These are horizontal spaces. Of course, it should be done in such a way that you can go smoothly from one to the other. So these are the fibers. These are the vertical vectors. So in some sense, a connection, the way I define, is a map which takes the tangent space of E and say what is the horizontal space that you associate to it. So this is a very general definition of connection. Now we come to the one which has strict relation with the gauge field. We consider a connection on a principal G bundle. So for a connection, a principal bundle, we require more. We furthermore require that the map induced on vectors respect, so this map, the G action. That is, we want that the horizontal space of the point that you have obtained from U acting on G, so this is a vector space, so there is well-defined push-forward map, is the push-forward map of the action of G on the horizontal space on U. So let me give a kind of intuition. Suppose you have your fiber bundle. Now this is a principal fiber bundle. So now you have also the action on the fiber. G acts on the fiber. So like before, you have your vertical, you declare your horizontal spaces. But now the point is you have one vector here, and this is a point in P. And now you act on this point, which is the U, it's called. You act with RG and you get the point UG. At that point UG, you also have a horizontal space. And what you want is that if you act in the obvious way, so by the push forward of RG on this vector here, you get the vector which acts here. Is here. So this is the definition. Okay. So the point is that because you have the action of G, we can characterize the spaces, the horizontal space HU, by now we come this a G valued 1,4 on P. So let's call omega. How is defined? Look, given an element tau which belongs to the Lie algebra of G, of course now you remember that the vectors are related to curves. And the curves I consider is the curve e to the exponential of tau times t. This clearly is it goes along G, and so this is a vertical curve on P. And so associated to this, there will be some vector on the fiber. But if you think a little, so this must belongs to the tangent space of E, because this, you remember, this is the usual stuff of the group G. And this is nothing but, again, your original element of the Lie group, of the Lie algebra. So now omega, which belongs to lambda 1 of P, so it's a one form, is a connection if the following property holds. One, if you apply omega, so this is one form, so you can apply to a vector which belongs to the tangent space. So and we apply in particular to the vector that we construct according to this curve. Well, so this is a form acting on a vector, give me, in the usual case, it would give me just some real number, but because it's Lie G valued, it will give an element of the Lie G algebra. And you want that this element is precisely tau. And the second property that you want is that if you consider the pullback of omega, due to the action of the group G, is nothing but the adjoint action of the inverse of G acting on omega, so in simple way is this. So if you require these two properties, the horizontal spaces HU are just the kernel of omega at U. That is the vectors B, which belongs to the tangent space of P at U, such that omega applied to this vector is 0. So we have characterized your horizontal spaces by one form which is defined in the total space of the principal G bundle. Can I move?
One second. Can I geometrically understand this last relation that geometrically that the projection along the horizontal axis would be 0 for in this picture above, for example?
Yes, you want if you have a vertical vector, now it's a vector along the fiber. Okay. So
Exactly, and this
uniquely. So you want that the projection of your vector V has along the fiber is 0. So that's what you would say is an horizontal vector.
yes. Okay. Yeah.
So let's see the relation of omega with gauge potential. On an open set, that's called UI, a local section SI, we consider a trivialization. So you take phi I of some u, which belongs to P, okay, is you map it into a point which is in the manifold and an element of the group, which is the fiber. And you ask that this satisfy the fact that U point in the total space of the bundle is equal to the image of P through the section SI times this element of the Lie group GI. So that, in particular, if U is exactly the point in which P is mapped by the section SI, GI is just the identity. So let me try to write in some kind of picture. I have UI, which is to which belongs P, so this is a subset of M, an open subset of M. And I have U, which belongs to pi minus 1 of UI. You have the section SI from here to here. Then you have a trivialization phi I, which maps into P, which belongs to UI, from which you start, and GI. Then it turned out that as the pullback of omega is now a form on UI, is a Lie valued 1/4 by construction on UI. And I don't know if you recognize, but this is a local gauge potential. So why? Well, remember that you have, so of course you have constructed this SI, so you have to start from UI, you have pi minus 1 of UI, you have on this, you have your omega, which is restricted to pi minus 1 of UI. Okay, so you have a projection, and now you construct, of course, the pullback. Sigma star omega, which will be constructed, will be now one form on UI. Notice that if on pi minus 1 of UI, one makes a gauge transformation, so U going into U times G, which means SI goes into some S prime I, which is SI times, let's call G. AI changed by A prime I equal to GI to the minus G. Let's call GI this one. Okay, maybe this GI. GI to the minus 1, AI GI plus GI minus 1 T GI. That is really like a gauge potential. So let me just end the intersection. UI intersection UJ. AJ in the intersection is equal to GIJ to the minus 1. AI GIJ plus G minus 1 IJ DGIJ. When you are GIJ are the transition function of B. Let me just make again a picture. Suppose you have your UI, which is a subset of M. Then you map into the inverse image by the projection of UI. Then you take a point P. You have a section, so we'll send to a point U here. And you will be, if you have a curve here, you will have a curve here. And now, so every point will be sent to some other point. You have a trivialization by I. And the interesting thing, okay, trivialization means here you have UI and here you have G as a vertical. And now you may, yes, it's such that every point U on this curve is mapped into just the identity of E, of G. I prove this relation. Okay, can I move?
Yeah.
Okay, how can I prove? This can be proved using the following, which I have no time. This I think perhaps is intuitive, but I cannot time certainly to prove it. If you consider the omega, so the connection restricted to the inverse image of UI is the following. You start from your AI, you make a pullback, which brings me back as a form on P. You act on GI minus 1 times GI, and you add G minus I GI. Why this work? Because remember you have your section SI acting on GI minus 1 pi star of AI GI. Remember that SI was sending in particular GI to E, always. Because as we said before, maybe in this, any point along this curve is sent to E in G, which means that this is E from the point of view SI. This is E, and S times pi star is the identity, so this is AI. And also SI star times G minus 1I EGI, since GI is E when you introduce SI, this is clearly 0. So it's true that, in fact, this is a function, this is a one form on P such that SI of star is equal to AI.
Can you move the page a bit down, please?
Oh, sorry. Now the crucial point is omega is globally defined on P, but AI not globally defined in general. On M, however, because omega is globally defined on P, omega I, when you restrict to pi minus 1 of ui intersection uj, must be equal to omega j when you restrict to the pi minus 1 of ui intersection uj. And now you apply this definition that I gave here, and you can do an exercise, which is not difficult. And then you can prove really the formula that I wrote before. Aj is equal to Gij to the minus 1 ii, Gij plus G minus 1 ij, dGij. So let me just perhaps finish. I don't know how much I have. So given omega connection, one can define its curvature. Big omega, which is d omega plus omega wedge omega. Remember that omega was an element of did you hear me now?
Yes.
Okay. It was one form P, so this is must be a two form in P, the curvature. And now again you have a section like before, you could like go, you perform the pullback of this form, you get some form Fi, which now will be a DG valued two form on UI. And again, omega is globally defined on P, and then this giving some compatibility condition for Fi and Fj in UI intersection J. And you can check that the compatibility condition is Fj is equal to Gij to the minus 1 Fi Gij. This is a good exercise. Again, you can check immediately applying SI star, use this property, and two lines of computation give me this.
Pieralberto, you have 13 more minutes roughly, like 12, 13 minutes.
Ah, okay. Well, plenty of time, actually.
Well, you started 15 minutes late, so I assume you
okay.
just drop them on top.
Okay. So can I move?
Yeah.
Okay. So now we want to, you have defined your connection we have seen that originally there's this interpretation of horizontal space. Now we have seen that you have an interpretation in terms of a one form, which is globally defined in the total space of the principal bundle. Now, and you also check that it's defined as a set of one form which are defined locally in the open set of covering of your manifold, together with some compatibility conditions. But there is so you have connected somehow this abstract geometrical notion to this thing which now transform like a gauge field. And now it's very natural that there will be another property which is important for the gauge field. You remember that if AI is a gauge potential or gauge field, in physics, how it appears for the first time, it appears in classical mechanics as the vector potential for the magnetic field. And how you take care of the fact that you have a magnetic field, so vector potential, let's call A, so a magnetic field. How you take care? You take care in a very general situation, just by taking your momentum P and making the so-called minimal coupling, which for solid state physicists may also be called Pilot's coupling. I don't remember anymore. So you can also apply to very strange function of P. Well, in quantum mechanics, modulo some constant, you know that P is related to the gradient, and so this is just this transformation, this minimal coupling give rise to a modification of the derivative, so they call the covariant derivative. And now the natural question is how you implement this in the bundle length, in the frame of bundles. Okay. The point is that the connection, as we defined, provides a way to connect smoothly vectors in different fibers. You see, a vertical vector is on that fiber, but now because they are horizontal, it moves outside of the fiber. And so how you make it? Well, you have chosen what is an horizontal plane through horizontal planes. So what is the picture that you have? So you have your base space. And now, for example, you start from a point P and you move along in your manifold M. But now on each point of this curve, you have your fiber. And you start from a point U, which is in the fiber of P. At that point, you know what is an horizontal space. And also, you know smoothly, the connection gives you smoothly which are the horizontal space everywhere. So what you can do is, okay, I start from your U, and I make a curve, which is gamma tilde, which is true horizontal plane, so in formula, given a curve gamma, so gamma is a map from 0, 1 to m, which send a point with the property that gamma 0 is equal to p. If you're in a fiber bundle E with connection, there exists, in fact, you can prove a unique curve gamma tilde in the total space E, which is horizontal. I mean, according this intuition, gamma tilde of 0 is exactly your point U, which belongs to from which you start in the fiber over P. And of course, the property of this curve in E is that it projects down by pi exactly in your original curve gamma of T. So what happened is that the map, sorry. Please tell me when I can move.
Yeah, it's fine.
So now the map which associate to gamma tilde of 0, so our U, gamma tilde of T, some point in the, remember again, this is curve, gamma here in M, this is P, and here I have this is U, this is the fiber, I have fiber everywhere. Here I have my horizontal spaces, and it will be some gamma tilde. The map which sends gamma tilde of 0 to gamma tilde generates an isomorphism of fibers. That's called tau gamma, which send me the fiber over U to the fiber over E over gamma of T, of course, where U was sent by this curve gamma tilde to gamma tilde of T. So it means that you can so you can do it for U, but you can do for everyone, right? On this fiber, you can do for everyone point. So you give me an isomorphism. This is called parallel transport. Now, if E is a vector bundle, on each fiber is a vector space, which is exactly what you need to define derivative. So if S is a section of E, we can bring a vector V, which belongs to S of gamma of T. Remember that now these points here, which are just vectors, because this is a vector space. Remember, this is a vector bundle. So you can, if S is a section of E, we can bring a vector V, which is in the image of the section S at the point gamma of T along the direction of gamma, and because gamma is a curve associated, there is an x vector, then you can bring this vector, which is on S of gamma of t, back to gamma of 0, which is u, by parallel transport. So how you have your vector, it was S of gamma of t. It is a point on the fiber, so you can bring it back through the tau of gamma from here back to here. And this object here belongs now to the fiber over u. So we can define the covariant derivative associated to the connection along the direction of x at the point P as a limit as t goes to 0 of tau of gamma t to the -1 s of gamma t minus s of gamma 0 divided by t. And you see, this is everything is well defined, because well defined because of difference in a vector space. So you see, yes, you have found that the connection in a vector bundle just exactly define a modification of the usual derivative into a covariant derivative. In particular, and just then I stop, if your E is just what we define as the bundle, which is start from P times V D, well, it turned out that this tau gamma in this particular bundle is strictly related to your A gauge field that we discussed before. And we define exactly locally a covariant derivative in the sense that the physicists use. So I think my time is finished.
All right, thank you so much, Pieralberto. Before everybody jumps ship, I have a few announcements on behalf of the organizers of the school. So first of all, the school is looking forward, the organizers are looking forward to meeting all of you next week in Maynooth. There is a booklet out which has been sent via email, and the booklet contains important information for you on many things, for instance, the campus in Maynooth, or how to reach Maynooth from Dublin Airport. And if you have any questions, please direct them at the organizers, and make sure to put Graham Kells in CC, or directly address him too. And with that, those are the announcements I had to make. So now I'm going to stop the recording. And if there are more questions, I guess.
If you have question, you can, of course, ask.
Yes, if you have more questions. I'm
registration.
going to stop the recording anyways, but I'm not going to end the session, the Zoom session.
Okay.